All right, good morning, everyone. Uh, so before we get started, are there any questions from the topics we discussed in the last class? Okay, so in this and the next couple of classes, we'll prove some theorems, which are basically tools to prove converse results in information theory. So we'll start off with the most powerful and the most widely used Fanos inequality, and we'll use this and in this class we'll use Fanos inequality to prove a converse for the channel coding theorem. And after that, we'll see some more tools which will mainly be used to prove converse results for broadcast channels. It will be further along the line in this course, but then it's still useful to know. And some of these tools are useful in other problems as well, but probably broadcast channels is the first place where you'll see an actual application of those tools. All right, so in the last class, I derived Fanos inequality, and this basically says that if you have m and m hat, which are jointly distributed random variables over some alphabet, let's call it capital M, if these are jointly distributed and you define the probability of error as a probability that m is not equal to m hat, then you can get a lower bound on the probability of error in the following way. So the conditional entropy of m given m hat is upper bounded by the binary entropy of PE plus PE times log cardinality of m. Okay, and now we'll use Fanos inequality to prove a converse for the channel coding theorem. Okay, and as I mentioned in the previous class, there are two main steps involved in proving the converse. The first is, of course, Fanos inequality, and the other is the fact that we're operating over a discrete memoryless channel. And for any discrete memoryless, so for a discrete memoryless channel, the mutual information is subadditive, or in other words, it tensorizes. What this basically means is that you can write the n letter mutual information between xn and yn as being upper bounded by the sum of the mutual informations between xi and yi. This holds for any joint distribution Pxn, so it doesn't matter if the xi's are correlated or not. The only property that we will use here is that the channel is discrete, is memoryless, basically. Okay, and so let's start by, we've already proved the first part, which is Fanos inequality. So let us prove the second part. So we start off with this quantity Ixn yn, right? And we know that this is h of xn. Sorry, let's write it in a different way. So I want to use the fact that py given x, pyn given xn basically is a product distribution. So this is h of yn minus h of yn given xn. Now I claim that this is less than or equal to summation I going from 1 through n h of yi given y1 through yi minus 1. So why does this hold? So is what I've written correct? And why is it, if so, then why does it hold? Yes, Raymond? So what property have I used here? Yes, anybody?
Sir, something related to Markov or something.
Not really. I mean, so this holds for any distribution, right? So, okay. So maybe I shouldn't have written less than or equal to. So I claim this is equal to this. Minus something. So there's one more quantity. So let's call it so h of yi given y1 through yi minus 1, comma xn. Okay, so why is this true? What property have I used here? So what rules for entropy have you already seen? What properties?
So we are using chain rule of
Exactly. So we're just using chain rule, right? So the chain rule says that h of x1, x2 is h of x1 plus h of x2 given x1. And this can be generalized to any number of random variables and even for conditional entropy. Right, so that's all that I'm using over here. I'm just using the chain rule to expand h of yn, and I'm also using the chain rule to expand h of yn given xn. So h of yn given xn is h of y1 given xn plus h of y2 given y1 and xn plus h of y3 given y1 and xn and so on. Right. So this just follows by chain rule. Right. So now I'm going to use another property. So I'll write this as summation I going from 1 through n, h of yi minus h of yi given y1 through yi minus 1 and xn. So I'm not going to touch the second term for now. I'm only going to write the first term as being less than or equal to h of yi. Why is this true?
like conditioning reduces entropy.
Conditioning reduces entropy. So conditioning reduces entropy, so I can write this as being less than or equal to this quantity. Okay, so now is the crucial step. I will say that this is equal to summation I going from 1 through n h of yi minus h of yi given xi. All right, and this is really the most important step, and here I'm using the fact that I'm operating over a discrete memoryless channel. So if I transmit over a discrete memoryless channel, then conditioned on xi, yi is going to be independent of everything else. So in particular, it is going to be independent of all the other xj's and all the other yj's. So for a DMC conditioned on xi, yi is independent of y1 through yi minus 1 and xn. So you should prove this separately. All right, and convince yourself that this is indeed true. So one way to look at it, so the way to prove this is to use the fact that p yn given xn is this product I going from 1 through n of p of yi given xi, plug it in this conditional entropy term, and then show that in fact this is equal to h of yi given xi for every I. Okay, but what is each term over here equal to? So what is this quantity?
Mutual information between xi and yi.
Exactly. So it's just the mutual information between xi and yi. Right, so this is equal to the mutual information between xi and yi. So, and that already gives us the result that we were looking for. So the mutual information between xn and yn is less than or equal to the sum of the mutual informations between xi and yi. And since we know that the maximum of the mutual information is equal to the capacity, for any distribution, this is less than or equal to n times the capacity. So each term is less than c, therefore the sum should be less than or equal to n times c. Okay, so is this clear? Was this proof clear? Or are there any questions? So in proving this, we're using three properties. The first is, of course, the chain rule, which is used to split h of yn and h of yn given xn. Second, once we split the mutual information, so you always start with what you want, right? So on the left-hand side, I have an n-letter mutual information. On the right-hand side, I have a sum of the mutual informations between xi and yi. So I have a sum of single-letter mutual informations. Right, and whenever you have an n-letter mutual information and you want to split it in the following way, what you do is you use the chain rule. You always start by using the chain rule, right? And then you see how you can manipulate each of these terms, right? So the first term, we know we want an upper bound, so we just use the fact that conditioning reduces entropy. So we already have one part of what we want. We want this. And we know that this quantity is less than or equal to h of yi. Right? And we get that very easily. The second part requires a little more effort because this does not hold. So this inequality, this equality over here does not hold directly. Note that in general, h of yi given y1 through yi minus 1 xn, so this is less than or equal to h of yi given xi This is true in general for any, irrespective of whether you're operating over a DMC or anything else, or any channel, you will always have this condition holding just by the fact that conditioning reduces entropy. But I can't use an upper bound for h of yi given y1 through yi minus 1 xn, because after all, I want an upper bound on this entire quantity and I have a negative sign sitting over here, right? So what I want is a lower bound for this quantity, but for a discrete memoryless channel, only for a discrete memoryless channel, this is equal to h of yi given xi. Okay. So in the case where you have a discrete memoryless channel, this holds. All right, and I'm just using that here. So that automatically gives me the mutual information between xi and yi, and I xi yi is always less than or equal to n times c, because you're using the same discrete memoryless channel for all the n channel uses, and the mutual information is less than or equal to c, because that is of course by definition. Any questions?
Sir, I did not get the discrete memoryless channel part. Discrete memoryless channel part.
Okay, so basically what we're using over here is that the xn given yn is equal to this. Okay, so let's try to do this. I'll do it quickly, but what we want to show that h of yi given y1 through yi minus 1 xn is equal to h of yi given xi. Okay, so this is what we want to show. So let's write down the left hand side in full. So what is this equal to? So it's sum over all xn, sum over all y1 through yi, right? Of what? So what is the definition of this conditional entropy?
Y1 intersection, Y2 intersection.
Yeah, so it's P of yi, y1 through yi minus 1 and xn times log 1 over P of yi, y1 through yi minus 1 xn. All right. So let's split this out. All right. So it's summation over all xm, summation over all y1 through yi. Okay. Of P of yi, comma xi. So I want all the relevant terms for now. Okay. So anyway, let's keep this as it is for now. Okay. So P of yi, let's pull out xi, y1 through yi minus 1, x1 through xi minus 1, and xi plus 1 through xn. Right? I've done nothing over here. I've just rewritten this thing in a slightly more convenient way. Okay, times log of 1 over, sorry, this should have been P of yi given y1 through yi minus 1 through xn. Okay, so that is the definition of h of yi given y1 through yi minus 1 xn. Okay, but the question is now, what is P of yi given y1 through yi minus 1 and xn? I claim that this is equal to, if it is a DMC, then P of yi given y1 through yi minus 1, x1 through xn, this is equal to P of yi given xi. So any suggestions? What can we use to prove this? What is the first step that you would start with if you have some quantity like this?
You can use the memoryless property that current output is only depends.
Correct. So that is really the property that you want to use. But then it's potentially possible that the yi, it's not just, so we know that, so the memoryless property certainly says that P of yi given x1 through xn, this is equal to P of yi given xi, right? And we also know that P of whatever y1 through yi given x1 through xn, this is also equal to P of y1 given x1, y2 given x2, and so on up to P of yi given xi, right? So using this, you should be able to show that this is in fact equal to P of yi given xi. So are these steps clear?
Yes.
All right. So the main property that we're using is that it is a discrete memoryless channel, and by definition of a discrete memoryless channel, this happens. Right. So in particular, P of y1 through yn given x1 through xn is P of y1 given x1 times P of y2 given x2, and so on up to P of yn given xn. Right? And this lets us show that this P of yi given yi through yi minus 1, x1 through xn is equal to P of yi given xi. Is that clear? How we're getting this step?
Yes.
The others?
Yes, sir. Yes, sir.
Okay. So since we have this, so P of yi given y1 through yi minus 1 and xn, this is equal to P of yi given xi. All right. So now we see that this quantity depends only on yi and xi, but this quantity depends on yi, xi, and a whole bunch of other things. So what you can do is you can just marginalize with respect to all of these other variables, because after all, this does not depend on on the other variables except yi and xi. So what is this equal to? Once you marginalize with respect to all the other variables, what will you get?
P of x I y i.
Correct. So once you marginalize, you will get P of xi yi. Okay, so this is equal to summation over xi and yi, P of yi xi log 1 of 1 over P of yi given xi. And what is this equal to? It's just h of yi given x, right? So if this were not a discrete memoryless channel, then we would not be able to write that P of yi given this is equal to P of yi given xi. So for example, if the channel has memory, for instance, if it is something like a frequency selective fading channel or any kind of a Markov type of channel, then we could not say that this is equal to this. Any questions? Okay. So now we've proved the two main steps required to prove a converse for the channel coding theorem. Okay. Let's try to prove the converse now. So whenever you're proving a converse, basically when you're trying to prove a weak converse, either for the point-to-point memoryless channel or for a MAC or for a broadcast channel, you always start with the following quantity. What do you want to prove? You want to prove something in terms of the rate, right? So you start with Kn, right? And this is basically equal to h of mkn, because we're assuming that the message is IID and uniform. Right? It consists of kn IID uniform bits. Okay. Now the first step is to somehow manipulate this in order to bring this to a form where we can use Fanos inequality. All right. So I somehow want to use Fanos inequality. So let's try to think of a way to bring this. So if I want to use Fanos inequality, I need to bring h of mk given mk hat. Right? I somehow need this plus something else. So there should be a something else over here. So what do you think that's going to be? Plus or minus something?
Minus PE of log m.
No. So right now I'm not using Fanos inequality. I want to apply Fanos inequality to this conditional entropy term. So that is why I'm introducing this. But
mutual information between m and m hat.
So is it going to be plus or minus?
That will be plus.
Plus. the mutual information between mkn and mkn hat. So basically what I'm doing here is that I have h of m. I want h of m given m hat so that I can apply Fanos inequality for this term. But then I have, so that will mean that I have this additional term which comes in, because the mutual information between m and m hat is h of m minus h of m given m hat. Okay. So now let us just apply Fanos inequality. All right. So I want to apply Fanos inequality because I want to somehow bring in the probability of error in between. Right? Because I know that if it's a good code, then the probability of error should be vanishing in it. If it's a bad code, then it won't be. Any questions? Okay, so I will use Fanos inequality to get h of PE plus PE log cardinality of m. So what is log cardinality of m equal to in this case?
Kn.
Correct. So it's equal to Kn because after all mkn is a sequence of kn bits. So log cardinality of m would be log of 2 to the kn, which is just kn. Okay. Plus the mutual information between mkn and mkn hat. Okay, so I have this now. I have these terms conveniently from over here, but then I don't know what is the mutual information between mkn and mkn hat, right? This is something that I cannot handle directly, but what I do know is that is what the mutual information between xn and yn is. So let us see. Can I write this statement? H of PE, so I'll keep the first term as it is, Kn plus I xn yn. So can I make this statement? Can I say that this is less than or equal to I xn yn, and if so, why? So recall what the block diagram looks like. I have mkn, which is being encoded, right, which is some deterministic function to give me xn. I'm passing xn through the DMC to get yn, and I'm decoding this to get mkn hat. Right? So these two are typically deterministic functions. This is some probabilistic map from xn to yn. All right. So can I say that the mutual information between m and m hat is always less than or equal to the mutual information between xn and yn?
Yes, sir.
Why is that true?
So data processing inequality we can use.
Exactly. So I can use the data processing inequality because mkn xn yn mkn hat, this forms a Markov chain. Right, so this forms a Markov chain, and therefore I can use the data processing inequality to say that the mutual information between m and m hat is less than or equal to the mutual information between xn and yn. Right. Now what can I do? Can I do something for this? We've just seen what this is
Summation
less
are equal to 1 to n I xi yn.
Correct. Which is less than or equal to
NC.
correct. So it's less than or equal to n times c. This is just step 2 that we have proved, right? Or the second tool that we have proved. So this is less than or equal to n times c. Okay, good. So now we have basically have everything that we need. So look at Kn minus n times c. So I'll take this n times c to the left. Okay, which is less than or equal to h2 of Pe plus Pe times Kn. Okay, so let me divide both sides by n and get Kn, and maybe I'll also take this to the left hand side. So Kn into 1 minus Pe divided by n minus c is less than or equal to h2 of Pe. Okay. So this is true for any encoder and any decoder, right? So here I have not used any assumption on the encoder and decoder. You could design the encoder in any fashion you wanted. You could design the decoder in any fashion you wanted. But this inequality will always hold as long as it is a discrete memoryless channel. Right?
Has to P by n, I think.
Sorry. Divided by n. Okay. So now, suppose that the left-hand side is so suppose that you try to operate at a rate below the entropy. Okay, sorry, below the capacity. If you operate at a rate below the capacity, what happens to the left-hand side asymptotically? What is the limit? N tends to infinity. Kn by n. So this 1 minus Pe. So Pe is always, let me try to make this look a little more easier. So Kn by n minus c. Okay, fine, doesn't matter. So let it be here anyhow. Okay, Kn by n 1 minus Pe minus c is less than or equal to h of Pe divided by n, right? Or so this should be less than or equal, or if I take this also to the left hand side, then this minus h of Pe by n should be less than or equal to 0. Right? So let me call the limit as n tends to infinity of Kn by n as r. Okay, so basically r into 1 minus limit as n tends to infinity of Pe minus c minus, what is the limit of this as n tends to infinity?
That becomes 0.
That becomes 0. So this is always less than or equal to 0. Right? Or the limit as n tends to infinity of Pe, if I take this to the right hand side, is always going to be greater than or equal to r minus c. Correct? Of course. So this is assuming that the limit exists. So in fact, I should be saying that the lim sup of this is less than or equal to 0. So the lim sup of Pe. So if I say the lim sup of Kn by n is r, then basically this holds. So the lim sup of the probability of error is always going to be greater than or equal to r minus c. Right? So if I try to operate at a rate below the capacity, then I know that this quantity is going to be negative. So this then I get a trivial lower bound that it is greater than or equal to 0. Right? It's greater than or equal to some negative quantity, but the probability of error is greater than or equal to 0, so it is not really very useful. But now what happens if I try to operate at an asymptotic rate which is above capacity? So if R is equal to C plus epsilon, then I get that the asymptotic probability of error is greater than or equal to epsilon. All right. So it means that the probability of error can never be driven down to 0. I cannot get, say, probability of error to be 1 by n or exponentially decaying in n or even decaying as 1 over log n. It will always be bounded from below by epsilon. Okay. So that gives us the converse part of the channel coding theorem. So given any sequence of encoders and decoders for which the asymptotic rate is greater than or equal to C plus epsilon. So if you take the lim sup, if the lim sup is greater than C plus epsilon, then the lim sup of the probability of error is greater than or equal to epsilon. If you take the lim inf being greater than or equal to C plus epsilon, then the lim inf of the probability of error will always be greater than or equal to epsilon. All right. So note that this holds for any sequence of encoders and decoders. It doesn't matter how you try to design. As long as the rate is above capacity, you can't have the probability of error decaying with n. All right, and just to do a quick recap, the only things we used were Fanos inequality and tensorization property. Right. So we started off by looking at the entropy of the message, which is basically equal to Kn. All right, and we simplified the entropy of the message to a form where we could use Fanos inequality. So this is a step that you will always do in any kind of a problem. If you want to prove a converse statement, then the first step is to write the entropy of the message and somehow simplify it to a form where you have h of m given m hat plus some quantity. Okay, and this quantity, whenever you see a quantity of this form, you just use Fanos inequality. And for this, you have the mutual information between the message and the estimate. And this can be upper bounded by I, x, and y, n. Yes.
Sir, how log 2 of cardinality of m is kn, sir?
So what is the message set in this case? So in this case, what is the message? Let's go back to, yeah, so here, right? So this is the message set, right?
Yes, sir. Sir, is it a fixed length coding means message?
Yes. We're always doing fixed length coding. Right? So okay, you're looking at a sequence. So of course, so it depends on n. So Kn of course will depend on n. But for a fixed n, for a fixed number of channel uses, you're designing an encoder, and the message length is also fixed.
Okay, sir.
Is equal to Kn. Okay, so once again, you have I of m given m hat, and you just use data processing inequality, and then just simplify. There's nothing more left to be done. Okay. So this is what is called a weak converse of the channel coding theorem. In fact, it is, at least for the point-to-point discrete memoryless channel, you can prove a strong converse, which in fact shows that the limit as n tends, if you try to operate at a rate above capacity, then the asymptotic probability of error is not just greater than or equal to epsilon, it is equal to 1. So it's impossible to decode the message. You don't just pay the penalty with a small probability of error. The probability of error is in fact asymptotically going to 1. So that is quite interesting, and it's basically sometimes, so you have this phase transition phenomena. So let us look at a very large n. Okay, so you look at a very large n and see the probability of error. So choose the best code for each n, and you choose the probability of error. Okay, the best code. So the best. So for each n, you choose the best possible encoder and decoder. Okay, and you look at the rate, the asymptotic rate, or let's just look at n by n. Okay, for really large n, if you operate at a rate below the capacity, then the probability of error will be very, very small. Right? So the probability of error will be something that's very small. It will be non-zero, but it will be like really, really small. Okay, but then what happens at capacity? So the behavior when you cross C, so below C, the probability of error is really small, but above C, the variation of the probability of error with the rate is not gradual. There's a sudden transition. So as soon as you try to operate at a rate above capacity, the probability of error will be close to 1. Right? So this is in fact the correct behavior of the probability of error of the best sequence of code. So for each kn, you have a different code, but then for each kn and for each n, you're designing, you choose the best possible code, whatever that is, then the probability of error will in fact be something like this. So below capacity, you can make the probability of error very small. Above capacity, the probability of error will be large no matter how you choose the encoder and decoder. So this is something like the phase transition phenomena. So the phase transition is something that occurs very frequently in physics, for example. So if you take a liquid, so let's take water. So above 0 degrees C, it's going to be a liquid, right? But as soon as you go below 0 degrees Celsius, it immediately becomes a solid, right? So there is this transition in phase. So this behavior is something like that. So below C, probability of error is very small, but then as soon as you cross C, it goes close to 1.
Sir, I understood that. I agree that after, if you want to achieve capacity greater than C, then there will be error. But this is something, seeing this phase transition diagram, it says that there is a gradual increase, as you said. So anything by which you can prove this, like it achieves one gradually, karke?
So it doesn't one gradually, right? It's a sharp transition.
Yes,
right?
it's a sharp transition. I thought that it might be like some increasing curve, but as
Correct.
it is a sharp transition, can we prove that there will be a sharp transition?
So why there is a sharp transition?
Yes.
So first of all, of course, we still have to formally show it, but then at least in the previous courses, you've seen that if you try to operate at any rate below the capacity, then the probability of error is very, very small, right? It's in fact, it is exponentially decaying in n. So you get 2 to the minus alpha n probability of error. Whereas in this case, so this requires much more powerful tools, and probably I will not have time to discuss it in detail. but I can either point you to references or maybe give a recorded video of the fact that of this particular property, right? So this
Okay.
is called the strong converse. And basically, yeah, so just above capacity, the probability of error is very, very close to 1.
Sure, sure.
It requires a separate proof, so I don't want to do it in class, but
Sure, sure.
I can give you a separate resources for those.
Yes, sir. Sure. Sir.
Okay. Any other questions?
Sir, I thought limit n tends to infinity probability of error equal greater than or equal to r minus c by r. Sir, one scroll up.
Okay. So maybe this I missed the term. Okay, yeah, that's correct.
By r.
Thank you for pointing that out. So it's less is equal to r minus c by r. So it's equal to epsilon by r. Correct. So whatever, it's greater than or equal to 0, right? It is some constant which is not vanishing with n.
Sir, then how it will be gradually increases to 1, sir, after c?
Correct. So that's what I'm saying. So we have proved this, but then this requires a separate proof. Right? So Fanos inequality itself is not sufficient to show that this statement. The proof of this is much more complicated. So that is why I'm not doing it in class, but I'll give you other resources to show this property. Okay, so this is a weak converse. So that's why it's called weak, because all you're able to show is that the probability of error is bounded away from 0, whereas the strong converse, which needs other tools, shows that the probability of error is asymptotically equal to 1 and not just something small greater than or equal to 0. Okay. Any other questions? Okay. So this was one application of Fanos inequality. Another tool which will be used to prove a converse for certain types of broadcast channels is this result called Mrs Gerber's lemma. It's a strange sounding name, and in fact Mrs Gerber's lemma was not proved by a Mr. or Mrs Gerber. It was proved by Weiner and Ziv, and the exact reason as to why this is called Mrs. Gerber's lemma is not known, but in the paper they say that they want to name this as Mrs. Gerber's lemma for some strange reason. Okay, and the result is basically a statement about the entropy of the output of a BSC. Okay, so suppose that I have a random variable x. So x, let us say, is Bernoulli Q, and I pass this random variable x through a BSC P. Okay, and the output of the BSC P is y. So the question is, given h of x, how large can h of y be? So I choose a Bernoulli random variable with a certain entropy. So I want to know how large can h of y be equal to. Okay. So one way of looking at the BSC is the following. You have x and you XOR this with a random variable z, which is Bernoulli P. Okay, so the BSC is equivalent to this sort of additive channel. The addition is not over the reals, but this addition is basically an XOR. It's an XOR operation. or if you know what it is, it's addition over the binary field. And the output is basically the XOR of the transmitted symbol and an IID Bernoulli P symbol. Right? So given this, we want to know how large can h of y be equal to. Okay, so if x is Bernoulli Q and z is Bernoulli P, then, or in other words, you pass it through a BSC P, then what can you say about y? Of course, this will be a Bernoulli random variable, but what is the parameter? What is the probability that y equal to 1? Anyone? So we saw this when we talked about degraded channels, remember?
P into 1 minus Q plus Q into 1 minus Q.
Right, so it's P into 1 minus Q plus Q into 1 minus P, which I will define as P star Q. Okay, so it is Bernoulli P star Q. So if I have X to be Bernoulli Q, then what is h of y equal to? It is just the binary entropy of P star Q, which is P star. I'm going to write this in a different fashion. So what is Q? So if X is Bernoulli Q, let us assume that all parameters are between 0 and half. So P is between 0 and half, Q is between 0 and half. So this is equal to H inverse of H of X. Do you agree with this statement? So I define, so if you look at the entropy function only for parameters between 0 and half, right? So this is an increasing function. It is concave, it is increasing. So therefore I can define an inverse for this function in the region 0 and half. And I can write h of y as h2 of the binary entropy of P star Q, which is P star h2 inverse of h of x. Do you agree? Any questions here?
Sir, but Q can be greater than half, right?
Q can be greater than half, that is true. But all I want is in terms of h of x, right? And Q is symmetric, right? So even if Q is greater than half, if I give you h of x, then whether Q is greater than half or Q is less than half, it doesn't matter. All that matters is what h of x is. Right? If Q is greater than half, then this is also equal to P star 1 minus Q. So H2 of, I claim that this is equal to H2 of P star 1 minus Q. So this is in fact an equality, and this is simple. This is not Mrs. Gerber's lemma, but a slightly more complicated situation is when the x and y are dependent through some random variable u. So there is some shared random variable between x and y. And now the question is, given h of x given u, how large can h of y given u be equal to? And that is really the statement of Mrs. Gerber's lemma. So this was proved by Weiner and Zip. And it says that, so here, h of y is equal to h inverse of h of x star p. This says that h of y given u is always greater than or equal to h inverse of h of x given u star p. Okay, and we'll prove this in the next class. Okay, so any questions?
Sir, I didn't understand how H2 of P star Q equal to entropy of P star of 1 minus Q.
Okay, so here, so which this statement?
Yes, sir.
So try to prove it. So you know what P star Q is, right? So plug it into the expression for the binary entropy. Plug this into the expression of the binary entropy and see whether they're equal or not.
Yes, sir.
Any other questions? Okay, so if not, we meet next week.
Sir, regarding the scribe notes, like, do we have to upload it in